Welcome to the second webinar on TwinCAT motion control, the second international webinar. So the main focus for today is an introduction to TwinCAT motion control and also to the PLCopen motion control function blocks. And as every webinar, if you have questions, you can ask the questions directly in the question tab on the GoToWebinar field. And we try to answer the questions at the end of the webinar. So the agenda for today is that I will give you a motivation on how we work in the TwinCAT environment with motion control. Then of course a general architecture, why we do things as we do it in the last years. And of course then especially an introduction to TwinCAT point-to-point motion control, which we call NC-PTP. And we will end with a summary. So first of all, the motivation. So we are doing motion control in TwinCAT environment since many years, and we see this as a standard in our environment, and especially in our modular software system. The motion control part has a lot of different blocks, as you see in the bottom. So we have motion control point-to-point, we have motion control NCI, which is interpolated but limited to 3 interpolated axes, and we have motion control CNC, which is limited to 5 interpolated axes, and a lot of transformations are available for this product. And we have the robotics package, which has a lot of different transformations for different robotic constructions. So we start with the different functionalities in the different packages. So in the point-to-point package we have of course the functionality doing gearing, camming, superposition and flying saw. And later on we will see what is the difference in this. We have the NCI package with the 3 interpolated axes and the 5 additional auxiliary axes. Programming style is of course the DIN 66025. And with the same language we also do the programming for the CNC. In the CNC package we have the limitation of 5 interpolated axes, and of course also a lot of transformations are available. The robotics package is based on the NCI package and has supports a wide range of different kinematic systems. Main topic for today is motion control point-to-point, and of course you see in the bottom also the PLCopen motion control blocks. So, next point is point-to-point motion control, and we start with the general architecture. So the general architecture is built out of different abstraction layers. So on the bottom we see the drive layer, so different drives, different shapes connected with different field buses. So the next layer is the field bus layer. Then on top of this we have the abstraction layer of our NC-PTP, so the different axes, the soft axis objects, and on top of course we have the application layer. So the application guys, they see the application layer, they do a move absolute, which is shown in the screenshot, and with the move absolute we are going into the soft motion layer. The soft motion layer generates the set points and of course does the control inside the software, but also of course sets the control inside the drives. And of course in between we have the field bus layer, which supports different field buses, so which supports the light bus, Beckhoff light bus, can open EtherCAT, Profibus, Profinet of course, and also Circus 2. And at the bottom again we have the different drives, different drive types, different motor types, and we support all of them with the same application layer. And this is one of the basic features we have. We have one application layer with one set of function blocks which can be used for all the different drives connected with all the different field buses. So to go more into details, we have for the TwinCAT I/O system, you know this, we have a separation between the logical layer and the physical layer, and in between we have the mapping. So you define a variable var1 which is a variable in the PLC, and this variable is connected via a mapping to a physical input or output, in this case an output, which is connected to a terminal and a channel on the terminal. So we do nearly the same also for motion control. So we have on the PLC side, we have the function blocks, which are connected to an access object, which is running in our NC-PTP driver, which is then connected via I/O mapping to a real physical access. And of course, from the HMI side, via ADS, via OPC, you always see the variables. You do not know on which field bus the variable is connected to which physical device. And it's the same on the motion control side. An HMI programmer always sees a logical access, which is then connected to a physical access. And also this in more detail. So we have in the PLC, we have the function blocks. The function blocks have mappings via a structure. So the NC to PLC and the PLC to NC structure. And of course covered with the access function blocks directly to the access objects, which are then connected via a physical mapping to the I/O layer. And you see it on the left side, we have a link to the I/O, which is linked logical access to I/O, and we have the link to the PLC, which is a link from the logical access into the PLC. So two mappings are necessary. So first mapping is from the access object to the I/O layer. Second mapping is from the access object into the PLC. So this is the general architecture, and of course we have to configure the motion control on the access side. We have to do the programming with the PLCopen motion control blocks, and then of course we have also we have to do diagnostics, and we will see later on how we do this. So first we start with the configuration. So first of all, motion control point-to-point is in software, which drives access for positioning mainly. We have different function blocks which communicate from the PLC to our NC, and the shape and the definition, the standard behind the function blocks is the PLCopen definition for motion control. The configuration of the access is completely done in TwinCAT 3, so you do not need external tools. It's completely integrated, and the real access are connected over mappings to the access objects, and the access objects again are connected with mappings to the PLC, and internally of course also via structures, different structures to the access function blocks. Because of these abstraction layers, we can support many different access types. We can do it with the same configuration, with the same programming, and of course also with different field buses. We are in the moment limited to 255 axes on one CPU. This is not really a limitation for machine builders, so we will keep this for the next time. We support different axis types, so of course servo axis, but also DC motors connected via different terminals, stepper motors with terminals, hydraulic axis, and also the XDS is supported also with the same function blocks. What function blocks are available? So a few examples. So we have function blocks for gearing. So we have slave axes, which are coupled directly to a master axis, and in between we have a gearing factor, and the gearing factor is set with a numerator and a denominator. So this is a 1-to-1, 1-to-2 gearing, which can be established. The function blocks are looking more or less the same. So we have for gearing and also for camming, we have a master input and a slave input, and of course at execute, and with the rising edge of the execute we start the gear in or we start the camming. And on the other side we have outputs which are more or less standardized. So we have always a busy, we have an active, we have a command aborted, an error and error ID, and we have special outputs, in this case an in gear and an in sync. So gearing is a linear coupling and camming is a nonlinear coupling. So for a cam, you define a curve, which is a relation between a master axis and a related slave axis. And normally there's a table in between. Then we have also a kind of coupling which is called flying saw, which is more or less the application behind, and the real meaning is that it is a gear in position, and so we have a position defined, we have a sync mode defined, and with this we can synchronize a slave to a master. And also here we have a master and slave axis as inputs when execute with the rising edge, and of course the same set of outputs. Superposition is another functionality we support, and with a superposition you can overlay a relative position distance additive to the main movement. So this can be used especially for conveyors. And then we have extended functionalities. So this is sometimes defined in the PLCopen motion control specification, but sometimes also outside. So we have function blocks in a special library. This is TCMC2 XFC library, and in this library we have functionalities for doing motion control with XFC, which means extreme fast control, and which is behind. We have of course EtherCAT as a field bus, and we have timestamp inputs and outputs, and also oversampling terminals which are supported in this special application. And one of the applications inside we do is dead time compensation. So with the directly using of the timestamps in the drives, and also of course in the master, we can do a time measurement, and with dead time compensation we can also support dead time compensation in the different axes. The correlation between time and position can always be used. So you measure a time and you get the position of a special axis with special function blocks. This can be used also for some applications behind. So one of the applications behind is touch probe, and so this is for the measurement side. You see on the right side on the bottom you see the XFC touch probe function block, and it can also be used for realization of a digital cam controller. And on the left side you see MC digital cam switch, which is a cam switch using XFC functionality. So what are we doing behind? So go more into the details. So behind every axis in the soft motion layer, we have of course a set point generator which calculates position and speed. And of course we have different controllers, so position control, velocity control, and you see in the block diagram we have of course also the dead time compensation, we have limitation, we have scaling for inputs and outputs. And so this is the control loop, the closed loop control loop, which is implemented in software and in hardware. To see it more in detail, so we have the set point generator and the dead time compensation, which is always done on the PC in software. We have the position controller and the limiter, which is more or less normally done on the drive. We have velocity pre-control, acceleration pre-control, and of course also the scaling and limiting of the outputs. And on the way back into the PC, we have of course the position measurement, and of course with the position measurement also the calculation from encoder values to physical values in meter or millimeter. So more or less 90% of the servo axis do position control on the drive. So this is the normal thing, but you can also do position control in the PC. So these are the different control loops, and of course on top of the controllers we have the set point generator. We have a 7 phases jerk limited set point generator, and of course we calculate speed, and we have also an override functionality for speed. So with the override you can lower the speed. And we have some implemented controllers, so you can use the P controller, the PID controller, with special settings, and you do not have to implement the controller, so the controllers are implemented. The only thing you have to do is to set the parameters, to determine the parameters for the different controllers. So to do this parameterization and configuration in the system manager part of TwinCAT 3. So first of all, you have to set some parameters. So for maximum velocity, reference velocity, manual velocity, scaling factors, controller parameters, and so on. And you do this for all the axes in the same way, in the same configuration way. You have to define the target positions, and you have the possibility to move an axis in manual mode. You have the manual buttons on the bottom. You see the screenshot where you can move the axis manually. And of course, you have to set the override. So these are the main settings you have to do. And if you have a Beckhoff axis, an H5000 for example, then the complete calculation of all the parameters, scaling factors, and so on is done automatically, and then you can start an axis, an X5000 axis with the motor in less than a minute. Of course, you need to define the dynamic behavior of an axis, and you can do this, the ramp up time. You can do this by selecting a special profile, or you can do this directly, of course, by calculating the parameters. Last but not least, it ends, of course, in parameters for acceleration, deceleration, and jerk. You can see just all the parameters in the parameter tab of the axis. You see on the left side the name of the parameter, and then you see the offline value. So this is the value when you start the application. So when you start activating TwinCAT, then we start an axis with this offline parameters. And of course, you can change the parameters. So we have also the online view. So if you change the parameter with a function block, or if you change the parameter with an ADS command, also from the HMI, you will see this in the online parameter set. And of course, on the right side, you see the unit which is used, so millimeters per second, and so on. So this is the set of parameters. It's a long list of parameters. We have different categories, so you can easily find all the parameters in this setting. So this is configuring the axis to do the setting of the different parameters, and of course, next step is to do the programming of the axis. And for the programming of the axis, we support the PLCopen motion control standard. And Beckhoff is also a member of the PLCopen group, of course, and we are also actively working on in the PLCopen motion control standard. So the idea is to use IC 61131, which is the standard for doing programming in PLCs, and to have a compatible programming interface for motion. We start with this in 1998, 1999, to do this in the PLCopen group, and in the group for motion control we have, of course, vendors, so like Beckhoff, Siemens and others, but we have also end customers like Tetra Pak, which starts defining the different function blocks for doing motion control point-to-point. And the idea was, of course, to have hardware-independent programming and, of course, vendor-independent programming. Same look and feel for all the function blocks. I told you before, we always have an execute for starting a movement or functionality, and we have on the output side always the same set of outputs. IC 61131 is, of course, the base. We have, of course, also extensions planned for different things. You can look to the different PLCopen standards. There's also an application guide available. And of course, also in TwinCAT, we support the motion control function blocks from the PLCopen, but we have also done extensions to this. So we have also TwinCAT specific access function blocks. And of course, we are always working on this, so we always extend this. We have more and more new functionality also done in motion, PLCopen motion control function blocks. We are standardized, of course, in the PLCopen group for our motion control applications for NCPTP, but also for the hydraulic axis. So we have two different products standardized in the PLCopen. A complete set of function blocks is defined in the PLCopen standard. So we have administrative function blocks and motion function blocks. For administrative function blocks, of course, we have a power function block, a reset, and different other function blocks. We have, on the motion side, we have, of course, move absolute or move relative, but also a position profile, a velocity profile, and so on. And for multiple axes, we support, of course, also cam in, gear in, phasing, and so on. What you always need is a power function block. So the power function block is the function block which does the software enabling of the axis. And you can do this for the direction positive or negative. And of course you can do a general enabling, so have a different set of inputs, enable inputs, and you see the function block screenshot. We have also a set of outputs. So this is a function block you always need, and you can start the axis, and then you can do a move absolute, a move relative, or one of the other function blocks. So this is the programming way. So programming we do with the PLCopen function blocks. We have extensions to the PLCopen function blocks. And of course, what you always need is to do diagnostics. And of course, also for the diagnostics, we have a lot of functionality. Of course, you can do the diagnostics in the PLC, so you can monitor the values. You can set breakpoints if you want. You can do a power flow if you want. But we have also additional diagnostic functionality, and one of the tools we also support is, of course, the scope. But we start with the screenshot of the online view of an axis. So this is very easily done. So it's one tab, the online tab, where you can see the different informations of an axis. So if the axis is ready, if it's calibrated, has a job, is moving, not moving. You see the physical status, as it's in target position, in position range. You see the enabling flags, and of course you see also the actual position, the current position, set point position, and of course the velocity and override settings and so on. So this is available for all the axes in the same view, and this is the online tab in the System Manager part. And additional information, graphical information, can be you can get this with the scope, and this is also easy in TwinCAT 3. So we can add a new project, a measurement project. And the measurement project has templates, and a special template is a template for motion control. So this is prepared for motion control, and all the settings and all the things you want to sample for an axis are integrated in this template. So it's very easy to use this template, especially for motion control. And with this template you can easily see the position, the velocity, the acceleration, and of course also the lag distance. So this is really one click to do this for an axis, very easy. So we had a general introduction of our architecture. We had the configuration part, the programming part, and also a short screenshot on the diagnostic part. And we will now sum up this presentation with some points. So one of the points is, of course, that Beckhoff, we have a long, more than 25 years experience in motion control. We do this on a PC-based control. So motion control is running in software, in our NCPTP package, and also, of course, in the NCI and the CNC package and the robotics package. We do from point-to-point to robotics, a continuous development in engineering and in runtime. And you see this in the configuration, you see this in the diagnostic part, but also, of course, in the programming part. In TwinCAT 3, we do this completely integrated in the Visual Studio. So we have one engineering framework with configuration, programming, and diagnostic. We are open for different axes, so we support different axis types. Servo axis, of course, stepper, DC motors, but also the XDS system, which is also a motion controller. And we support also different field buses. And we also support, of course, non-Beckhoff axis. We all do this with the same configuration. So we do the configuration in the system manager part, and it is identical for all the different axis types, and it's field bus independent. And we do the programming also independent of the field bus and independent of the axis type. And we do this with PLCopen motion control standard blocks. And additionally, of course, we have diagnostic for an axis, so you can see the monitoring of the axis, but you can also see the scope functionality. So I'm ready with my presentation, and I will try to answer some of the incoming questions. So the difference between TwinCAT 2 and TwinCAT 3 for motion control, it's really the same. So we have the same set of function blocks, we have the same functionality, we have the same integrated diagnostic functionality. So no difference between TwinCAT 2 and TwinCAT 3 for the motion control part. The application guide for PLCopen motion control, you can get this very easily from the PLCopen website. So there's a part 3 or 4, part 3 I think, which is in the motion control part, which is defining application guides for doing motion control with PLCopen motion control blocks. There's one question regarding touch probe functionality. So the touch probe functionality can be used in different environments. So touch probe can be used, of course, with the touch probe inputs on the drive, but we can also use touch probe with special terminals, so normally timestamp terminals, which is then a distributed touch probe application. Okay, I think I do not miss questions, and I will close the webinar, and you will find the webinar in the next days also on our webpage. So have a look at beckhoff.com/webinar, and you will find this webinar, and you can see it again, and you can hear it again, of course, but you will also find in the archive different other webinars. I thank you, and we will see us perhaps for the next webinar.